So I gave you guys, after the class, after the test, yesterday, was the history of the development of the atomic theory. Okay, today, I'm actually going to go into details of what we understand and what we know. So we're working on the modern theories. Do you guys know why this is considered a theory? Right, it's not 100% confirmed, okay? And just like it was changing over the past, we continue to learn more and more about the atoms and how they work. And that's informing us. And as we get informed by that, the theory morphs and it warps and it changes, okay? So this is an ongoing developing theory. It's gaining more and more detail. Does that make sense? Okay. So, basic structure of the atoms contains three main particles. Mind you, the electrons, protons and neutrons in particular are actually made up of other particles, just so you're aware. They're not just a proton and just an electron. They actually do get made up of smaller things. They're called quarks and bosons. And the atom in the inside is actually held together by gluons. I know, really. They glue the particles together, hence they're gluons. So we're learning more and more about the atom every day almost. All right, electrons, location is outside. It's in the electron cloud. And the electron cloud, you have to understand, is a probability cloud. Those electrons move so quickly and so fast that they're a blur. So electron cloud is where we expect to see them, not necessarily where they are at. Does that make logical sense? Because they're moving so fast, they're kind of a blur. Well, and the cloud does have different shapes, just be aware, we'll talk about that a little later. But for now, I'm going to use the S shape, which is just a sphere, okay? They actually look like dumbbells, and you guys have seen balloon arrangements where they have like 3 balloons together, 4 balloons together. That's actually what the electron clouds end up looking like. The more layers you add to it, it's the wildest thing. All right, so electron outside, which is electron cloud. The charge is a negative. The mass is negligible in comparison to the proton and the neutron. It does have mass, I don't want you to think it doesn't, but it's so tiny, for our purposes, we're going to ignore it, because we're looking at protons and neutrons as well. All right, proton, where's the proton located?
On the inside?
Yep, on the inside, in the nucleus. I'll just spell this somehow. Same thing with the neutron. What's the charge of a proton?
Positive.
Yeah, positive. And mass is 1 atomic mass unit. Or, not to be confused with atmospheres. Make sure if I write what it does, AUM, not ATM. AM unit. It's MAU. So AMU. There you go. Atomic mass unit. Neutron is also in the nucleus, has a neutral charge, and it's also 1 atomic mass unit.
Neutral meaning can be both?
No, neutral means it has no charge.
No.
It's neither positive nor negative. It'd be cool if we could switch, but it has no charge on it. And that's because of what it's made up of, but we won't get into that for this introductory course. If you're interested, you're more than welcome to look that up, what they're made up of. It's pretty cool.
Question.
Yes, sir.
So it's asking like what the subatomic particle used to define an element and explain why this particle is used.
We're working on that next. I'm getting there. I just explained the particles that are in there so far. Make sense?
Yeah.
Alright. So now let's talk about some atomic facts, and this actually speaks directly to your question. So each type of atom has a unique number of protons, and you can see it in the periodical chart. The helium, which is H, has a atomic number of 1. That means it has 1 proton. All hydrogens have 1 proton. If you add a second proton, all of a sudden becomes helium. It's no longer hydrogen. Because hydrogen has 2 protons. Does that make sense? Silver has 47 protons, and gold has 79. So every type of atom has a specific number of protons. So it's the protons that is what we use to define what the atoms are. Does that make sense? Okay, so have you caught that?
I think so.
Alright, so protons. By the way, as many number of protons as you have the same number of electrons. So if there are 2 protons, how many electrons are you going to have?
2.
2. If you have 5 protons, how many electrons are you going to have? 5. So they're exact same number. That means your overall charge for each atom is neutral. Does that make sense? And I should say overall charge of the element, the atom in its element form, not when it becomes an ion. That's a different thing. Alright, atomic number tells you the number of protons that you have in that particular element. The atomic mass defines the number special of grams in 1 mole of atoms. We'll talk about that in a minute. Can you see atoms with the naked eye?
No.
Do you see it with a microscope?
And
What type of microscope?
scientific.
They're all scientific. Any ideas? There is a specific type of microscope that you can see it with, but it's very specialized, and I'm almost 100% sure there's nobody in this room who's seen one except for me. They're called electron scanning microscopes. Those ones we have seen the influence or the outline of a atom, but you haven't actually seen the atoms themselves, which is kind of cool. Because of that, we need to be able to collect enough of these things together in one clump to be able to measure it. Manuel, you're distracting the ones next to you. So let's talk about Avogadro's number. Okay, so you define one mole. MOL, not MOLE. So it's a different type of mole. To be 6.022 times 10 to the 23 atoms. Does it make sense that it's gonna have a huge number of atoms in order for us to be able to clump it together to measure it? Yes, no? They're so tiny, we have to use a very special microscope that throws electrons at it to even get an idea of the shape. We're going to collect a ton of those together to be able to actually be able to weigh it. Does that make sense? Alright, because they're so tiny. Alright, so this is the way we use to count the tiny particles. Just like when you have you've got 1 dozen. Equals 12 pieces. 1 mole is 6.022 times 10 to the 23 atoms. Alright, so it's just defined. Just like a dozen is 12, a few is 3, a couple is 2, half a dozen is 6, yeah. So we've got a number of words that we use to define clumps. A baker's dozen, do you know what that is? 13. Yeah, it's 13. So just like we use a term to define a certain number, that's what we're doing with a mole. A mole is just 6.022 times 10 to the 23 atoms. It's just a collection. Does that make sense? Is that confusing to you? Okay. Some people get confused by it. It's just a straight up definition. Alright. Did you know that not all atoms, even if they are of the same type, have the same number of neutrons? Did you guys know that? Yeah, that's kind of cool. Another fact. Okay, so I wrote it like this. Not all atoms with the same number of protons have the same mass, but they are still the same element. Okay? Any idea what's changing? The protons are the same, but they have a different mass. What is changing? The charges are staying the same. Good guess though. Look at our particles, we have electrons, protons, and neutrons. The number of protons are staying the same. Electrons don't matter. What? Yes, neutrons. Some have more neutrons than others, very good. Okay? So, some have more neutrons. These are called isotopes. Okay, my spelling is atrocious. Isotopes. So, atoms with the same number of protons but different number of neutrons. Let me give you a famous one. We have hydrogen. So this is your atomic number. The bottom one is your atomic mass. But this is not the only type of hydrogen we have. We also have a type of hydrogen that looks like this. And they call it deuterium. What's the difference between this hydrogen and that hydrogen? Yeah, the two, which is, means the atomic mass of 2. Which means it has what in its nucleus? Besides the proton, it has a, yeah, neutron. So this deuterium, which is quite rare by the way, deuterium has a single neutron in addition to its proton. It actually has very interesting behavior. Did you know that if you freeze deuterium, the ice from deuterium actually sinks? It does not float. For water made with regular hydrogen floats. That's why they call it heavy water. It's because it'll actually sink. Tony said that they don't usually take frozen deuterium and put it into water. They take frozen deuterium and put it into liquid deuterium to demonstrate that. So when it melts, they don't lose their deuterium. They don't have to actually filter it again. Some isotopes are more common than others. You guys have heard of carbon-14? For carbon dating. Alright, carbon-14 is quite a common isotope. And you're ingesting carbon constantly, your entire lifetime. When you die, you stop ingesting it, and that's why they use it to date things. It's because after death, there's no more input of that carbon-14. That carbon-14 is, it's radioactive in a very mild sense. It deteriorates over time, and so the rate at which it deteriorates can help them figure out how long ago what they're looking at died. Okay. Assuming, making a huge assumption, that the rate remains constant, and that's a whole other discussion for another time. All right, any questions on this so far? Let's do a few calculations with this. You got a periodical table on the inside of your textbook. We're gonna use this to our advantage. Let's do carbon-14. I want to know the number of electrons, the number of protons, and the number of neutrons. That's in carbon-14. Carbon is what element letter? C. What's its atomic mass? Sorry, atomic number.
14.
Sorry, I just realized I wrote it up wrong. What's the atomic number on carbon? 6, if you look up the periodical table. Alright, so how many protons does it have? 6 protons. Which means it has how many electrons?
6 electrons.
6 electrons.
14.
Well, that's a good question. The 14 is what we're going to use to figure out how many neutrons there are, because this is the atomic mass. Your atomic mass is made up of protons plus neutrons. Does that make sense? Alright, so I'm going to take my 14 and I subtract off how many protons there are, which should tell me how many neutrons there are. Does that make logical sense? Okay? So if I have 14, I subtract off 6, how many? 8. Yes, 8. So I have 8 neutrons in that one. Where if I do carbon 12, which is the usual carbon, yes, it would be 6. So my electrons are 6, my protons are 6, and my neutrons, yep. You know what's hilarious? I know people say that. This is the most common carbon, it's what makes us up.
Oh, really?
Yes, that's why, it's one of the reasons why it's called the number of a man. Or number of man, but a lot of our life is carbon-based. So there's a lot of that. So you can read into it what you wish. I don't get too conspiracy theoristic on this because, you know.
Bruh.
Can you, make sure you pop the door open so you can get back in. Are there any questions on how to do this? So you just take your atomic, by the way, the atomic number that's in your periodical table, look at carbon, when I say carbon. What number is, atomic mass number is underneath carbon itself?
1.0107.
Yes, 12.1017. What they're doing is they're taking the average of all the carbons and they put them in here. Does that make sense? That's why it's not a whole number. And they do it by percentage. So your atomic mass on your periodical table is just the average of all of the isotopes put together. In fact, if you look, there's not a single one here that is a whole number. You see that? You see a single whole number underneath these?
Yeah.
What's today's assignment?
It's just the, I didn't write it up.
Page 127, 1 to 16.
Oh my gosh.
What about your dad?
I said gosh.
Uh-huh,
Still,
that comes
you just
from,
started referring to God.
Oh my Jacob.
I didn't know he was yours.
This one.
Yeah, he is.
Yes.
So, how do we determine the molar mass?
Done.
Wait, I need.
Uh,
No, that's
The 4 elements that it gave us.
You add neutrons and protons.
so much for. You know,
Oh wait,
I'm
the
not-
molar
I'm not
mass for
complaining.
what? What are you talking about?
Question number 8.
You look it up the periodical table.
Okay.
That's your atomic mass.
Oh, okay. So it's the
Molar mass
exact.
and atomic mass are the same.
Yeah, wait.
Where the heck is magnitudes?
And actually, I only want you guys to do 1 to 12, don't do, to 16.
Okay.
Because I have something else for you as well on that.
No, if you want, what's the,
Maybe they didn't.
Wait, just wait it.
Yes, sir.
On the board, what question did you do?
I didn't.
You did?
Those are just notes.
No, but somebody needed to answer the questions.
I know that.
Because they're notes.
The notes are supposed to help you figure out what you need. These are not anything, actually, that's not, I guess that's not true. Carbon 14 is talked about on number 15, number 5A.
Is that the right answer? Oh wait, never mind. Yeah,
Yes.
it's all up for.
Explain the masses, how the masses might differ. We already talked about 4. Calculate the number of neutrons. We already talked about how to do that. Define the unit used for atomic masses. I already talked about that when I atomic mass units. Avogadro's number, it's up there already. The molar mass you pull directly off the periodical table. If you lose an electron, what's the overall charge of the atom going to be? If you lose a negative, it becomes positive, yeah, it becomes positive. And they want you to predict which isotope is nitrogen is more common. 14 or 15 hints, look at the average mass, that should tell you. That'll give you an idea whichever one it's closest to, that's the one that's most abundant.
And what God is?
11.50.
Already?
Mhm.
You've been doing it while I was talking. For number 11, you're gonna need my help on that one. Alright, they want to know which one of these contains more atoms. 3 grams of iron. How much of the next one?
What?
2 grams of sulfur. Alright, so I'm gonna set up a chart for you. Grams per mole. There'll always be 1 mole on top. The grams is what changes. This is where you're gonna go to your periodical chart. So if you look at your periodical chart, how many grams are in iron, Fe? Number 26. How many is there?
3.
Well, 3 grams, right, but I'm trying to find the molar mass. So you need the periodical chart for that. So Fe is 26. How many, what's the molar mass for it? Did you say 55.845 for Fe? It's Fe. Number 26. Fe, number 26, my number 26.
55.45.
Yes.
55.45.
Did you find it?
Yes. Where is it again?
So that's gonna be,
55.845. Right?
so what you're gonna do is you're gonna take the 3 grams, you're gonna divide by the 54.845 to get your number,
3 grams?
for 3 grams. For sulfur, I've got 2 grams. Sulfur is
What number is that?
16. Sulfur is 16. What do I have for that one? Alright, so you're gonna take 2 and divide by 32. Whatever, and then you look at which one is bigger.
No, we don't round by, we don't multiply or divide by the.
Well, it's gonna be, we're gonna do 2 significant digits when we're done.
But,
When you're finished. So you take the number of grams, which is 3, and you're gonna divide by what's on bottom, which is 55.845. I don't know what that number is. But then you write that number down. Then you take 2.0, divide by 32. Write that number down. Then you compare. Tell me which one is bigger.
But why do you only divide by 32 on that one, and then on that other one over there, you do all the numbers?
Good question. This is the atomic mass for iron, specifically for iron. This is the atomic mass for sulfur. That's iron, that's sulfurs, that's why they're 2 different ones.
wait, so top number divided by bottom number.
Yes, 3.0 divided by 55.
Just 55?
Because
That's
what
nice.
I'm trying to ask
Or
is like,
55.845?
why in the, for Fe, you divide by 55.845, you divide by all
Correct.
five numbers. But for sulfur, you only divide by 32 and not 0.6.
No, I'm 32, et cetera. I'm dividing by
Oh,
both.
okay.
I'm doing both because then I round to only 2 numbers.
Okay.
Does that make sense?
Alright.
Because they only gave me 2 significant figures here, 2 significant figures here. I can only give them 2 significant figures. I can't give them more. That's why. Good question. Sorry, it was, yeah, it's supposed to be consistent. Alright,